Hello, it's Mr. Sarusa, and today we're going to talk about the polar equations of conics. So, mostly we're talking about the same things that we've talked about before. The directrix we talked about with the parabolas, the focus we had with all three conics, parabola, ellipse, and hyperbola, and so I'm introducing a new term, and that's eccentricity, and that's this ratio here. The eccentricity of a conic is the ratio of the distance from the point to the focus to the distance of the directrix to the point. And so if it's a parabola, those two are equal, and the eccentricity equals 1. And we know that already because that was the definition that we already had for parabola. But now we're going to bring that into an ellipse. And if the point is closer to the focus than it is to the directrix, then that's going to be an ellipse. And if the point is closer to the directrix than it is to the focus, then that's a hyperbola. And you can see down here that, in other words, if the eccentricity is less than 1, it's an ellipse. And if it's greater than 1, that's a hyperbola. We also can have a new ratio. It's just C to A for eccentricity. You can use that for the ellipse and the hyperbola. And that's just saying the center is closer to the focus than the vertex if it's an ellipse, and it's closer to the vertex than it is to the focus if it's a hyperbola, which you already knew just looking at the picture. So let's derive an equation for the different conic sections, and they all use the same general formula. It just matters what the eccentricity is as to which one it is. So let's go to a polar graph and draw the directrix. So I'm just going to draw some random directrix here, and so that's it. The directrix could be any vertical or horizontal line around here on either side of the pole. So remember, the pole is right here, and that's where we're going to put our focus. Okay, so think of that pole as the focus, and then we just need to put in some point. So I'm just going to randomly put a point in here, and that's our xy. So remember, what we're looking for is we're comparing the distance from the point to the directrix, that's here. So point to the directrix. And then we also need to know the distance from the point to the focus, and that's this one. So point to the focus. And so the one I just did is much easier, the point to the focus, because really that's just r, right? That's the radius. So I'm going to actually just get rid of this and just call that r. That's r, and I can make a triangle out of that, and then now you can kind of see where the picture's going. And then the distance from the point to the directrix, I drop this line down, and I'll call this q, and it's the same distance to the directrix. So I'm going to call that distance from the focus to the directrix, I'm just going to call that p, and then this other horizontal part that I just drew in, remember, that's just a triangle, so that's r cosine theta, because that's the horizontal component. So if I add those together, I get the distance between the point and the directrix. So let me start deriving the equation, and I'll start off with that definition of eccentricity as the distance from the point to the focus over the distance from the point to the directrix. And so we just came up with the distance of the point to the focus as r, so that's easy. And the distance from the point to the directrix is p plus r cosine theta. So I just wrote in what the two things I determined. And now what I'm going to do, I have my e here, I'm going to multiply both sides by the denominator. So e times p plus r cosine theta equals r. And then I'll distribute, so EP plus ER cosine theta equals R. And then I'll subtract the ER cosine theta to get the R's on the same side. So EP equals R minus ER cosine theta. And I'll factor out the r's. That's why I brought it over to the other side. And get 1 minus E cosine theta. And then finally I divide by that 1 minus E cosine theta on both sides. And so what I left with, something solved for R. So our final equation here, R equals EP over 1 minus E cosine theta. And so really important to note that this is always going to be 1. And if you set that equal to 1, then you can calculate out, or you can just observe what E is, and then calculate what P is based on the EP in the numerator. Okay, hope that this was helpful. Talk to you later. Oh, sorry, one last note. This is a really useful page right here. Make sure you know all the different types, and this will these different forms are just depending on where the directrix is. So I did the one where the directrix is to the left of the pole, but also you can have a separate one for the right of the pole, parallel to the pole, and or below the pole, above the pole. So very useful form right here. Okay, this time I'm really done.